Hello, everyone. I'm Reichiro Nakano. I'm a software engineer at Infostellar. So that's a small startup based out in Tokyo, Japan. Today, I'll be presenting our open source project, communicating with satellites using Starcoder, which is a lightweight GRPC server for managing GNU radio flow graphs. So here's a quick overview of this talk. I'll begin by explaining a little bit about what we do at Infostellar and how we came to need Starcoder. Then I'll actually talk about Starcoder, beginning with a brief explanation on RPCs, GRPC, and protocol buffers. I'll talk about the architecture and the key features. Then we'll move on to some real-life examples of how Infostellar uses Starcoder's features. And finally, I'll talk about the current state and a short roadmap for future work. So I work for Infostellar, and at Infostellar, our flagship product is called Stellar Station. I guess most of you have seen the presentation yesterday by SatNogs about their worldwide network of ground stations to communicate with satellites. Well, Stellar Station has the same concept. We're also a network of ground stations, although our focus currently is on commercial use cases. We're currently building out our network of ground stations. Right now, we're focused on commercial UHF and S-band, looking to expand into the higher bands over the next few years. But we also have something called Stellar Station Amateur, dedicated to tracking amateur satellites. Here's a screenshot from our amateur service website. The white squares are satellites that we're currently tracking, orbiting around the globe. And the white circles are online amateur ground stations. So now you can imagine there's a lot of work involved in building this network out. But one problem that is the main focus of this talk is that a single ground station must communicate with multiple satellites per day, all with different protocols. So in a single day, it could talk to a satellite using BPSK, FSK AX25 packet radio, NOAA weather satellites, LRPT, and it has to know exactly how to do that with roughly the same hardware in the ground station. So it's a perfect application for software-defined radio. Now, initially, our ground station software, which is written in the Go programming language, did all the work necessary, from managing satellite passes, moving the rotator, communicating with the cloud. We also had it do digital signal processing. So we got about as far as writing decimation, FIR filtering in Go when we realized that we're just reinventing the wheel. And why aren't we just using GNU Radio when it can do all of that and much more? So eventually, we realized that we had to use GNU Radio. And so our problem became, how do we easily and programmatically start and stop multiple GNU Radio flow graphs and interact with them? So where interacting primarily means sending commands to the flow graph. For example, if you wanted to send a command to a satellite and send some modulated payload to the GRPC sink, or if you wanted to get packets from the flow graph, like if we wanted to get decoded AX25 packets from a satellite and bring it back from the flow graph to our Go software for our business logic to kick in. One way that we decided to do that is through remote procedural calls, or RPC. Put simply, RPC is a way for a program, or rather a process, to communicate with another process. Now, this could be on separate servers over the internet, or just two Docker containers in the same host. But the point is, two separate processes are communicating. We see the usual flow of an RPC process in this diagram. The caller, the client process, calls a procedure on the remote server process and waits for a reply. This request is sent with the procedure's parameters over the network, so it's equivalent to a function in its input parameters. And the server receives this request. After receiving the request, the server does the necessary processing, constructs a reply, and sends it back to the client. And that's it. Effectively, the client process has called a procedure on a remote computer. So we decided that this is how we'd solve our problem. By having our Go software running in one place, we'd communicate with another piece of software running GNU Radio via an RPC connection. One alternative we explored to do this was to use the built-in control port in ZMQ blocks. After all, why not just use something built into GNU Radio itself? But this had a few problems. First, it did not solve our problem of starting and stopping multiple flow graphs. So that's something extra we'd need to manage ourselves by probably calling a bash process, running the Python flow graph from software. We'd also need to manage multiple Thrift and ZMQ connections. For every flow graph we run, we'd need to run control port on a separate port and have our software communicate with that. And with ZMQ sinks, we'd need to open multiple ports for every kind of data that our flow graph returns. So that kind of thing will quickly get annoying to manage in software. Finally, we wanted to use PMTs for communication. And PMTs passed from ZMQ sinks are serialized via GNU Radio's arbitrary serialization format. So the calling language would need to know how to deserialize that. And right now, only C++ and Python know what PMTs are. So we decided that these problems are enough to build out Starcoder, which is a lightweight gRPC server for managing GNU Radio flow graphs in production. Before I go into the details of Starcoder, I'd like to briefly discuss gRPC and protocol buffers. So gRPC is Google's high-performance, open-source, universal RPC framework. So in that sense, it's similar to Apache Thrift, which Control Port actually uses. There's a quick overview of how gRPC works. To use gRPC, we first have to define the RPC service, its available procedures, and their corresponding inputs and outputs in what we call the protocol buffer format, protobuf for short. So protocol buffers are Google's language-neutral, platform-neutral, extensible mechanism for serializing structured data. Simply put, it's a way to define data structures. So here's an example protocol buffer file with the name greeter.proto that defines a single RPC service called greeter. Greeter gives us two RPCs, say hello and say hello again. Taking a closer look at say hello, we can see that it takes the argument hello request and returns hello reply as the return value. So hello request and hello reply are also defined in the protobuf. Hello request simply contains a single string called name, and hello reply contains a single string called message. Aside from strings, protocol buffers also define other data types like integers, floats, bytes, and it's up to you to structure your RPC call, inputs and outputs, whichever way makes sense for your application. So now that we have this protocol buffer file, we need a way to be able to use it in an actual programming language. And gRPC lets us compile the protocol buffer into a library that we can use directly into our language of choice. So currently, protocol buffers can be compiled to 10 languages, like Python, Go, C++, Java. So let's say we want to use Python. We use gRPC to compile this protocol buffer file into an importable Python library. And this is how simply we can use it. Say we want our client to call the sayHello RPC function on some remote gRPC server. We just import gRPC library, which is our auto-generated library, and we call gRPC library.sayhello, while passing it the hello request parameter, which is a Python class that is also defined in the auto-generated library. We can then print its response, which turns out to be an instance of gRPC library.helloReply. And that's it. From the point of view of the client, it's just a simple function call. gRPC hides away all the implementation details like the protocol buffer serialization and underlying network calls. One thing to note is that the gRPC server, the thing that actually does the processing for the RPC calls, can also be written in any of the 10 languages that gRPC supports. So the client could be in Python, server could be in Java. Everything the client and server need to know is in the single source of truth, the protocol buffer. One more thing, gRPC natively supports bidirectional streaming. So this means that instead of, say, calling a function with one request and one response, it can open a stream with the server, and it can send however many data packets it needs. And the server can also use the same stream to send back however many data packets it wants to. We use this particular functionality heavily in Starcoder, and is in fact another big reason we chose gRPC. Thrift, I believe, does not natively support bidirectional streaming. So from a programming standpoint, it's possible. We'd probably have to use something like polling and message queues to simulate a bidirectional stream, but it's much easier to just have something like this be supported directly by the framework. Now we can start to discuss the actual Starcoder architecture. First, notice that the GNU Radio flow graphs are run and managed by Starcoder, which itself is a gRPC server. Shown is the protocol buffer snippet that defines the Starcoder service. It just offers a single RPC call called runFlowgraph. RunFlowgraph takes a stream of runFlowgraph request and returns a stream of runFlowgraph response. You'll notice that it's using the bidirectional streaming API that we just talked about. Now, this is the usual way a client would access Starcoder. The client opens the gRPC stream by sending a runFlowgraph request. This first packet contains the name of the flowgraph to compile and run, and the set of parameters to instantiate it with. So by parameters, we mean the actual parameter blocks for a flow graph in GNU Radio Companion. After this first packet is sent, Starcoder starts the flow graph with the given parameters, and then the real communication starts. Using the same bidirectional stream, the client can just continuously send run flow graph requests to Starcoder. And this time, the run flow graph requests contain PMT messages sent directly to the flow graph. Since it's a stream, we can send as many of these as we want as long as the flow graph is running. And since it's a bidirectional stream, the flow graph can also directly send as many PMTs as it wants back to the client through the same connection. This is run flow graph response. So the communication just continues until the client decides to end the stream, after which Starcoder will take care of closing the flow graph and cleaning up resources. And since it's a gRPC server, multiple clients can just connect to it and start their own GNU Radio flow graphs. At the same time, one after another, doesn't matter. Now, I mentioned that these PMT messages are constantly being sent directly to and from the flow graph. What does this look like in the flow graph side? So Starcoder actually provides two blocks for this, the Enqueue Message Sink block and the Starcoder Command Source block, which are contained in an out-of-tree module called gr-starcoder, which is in the same repository as Starcoder. So the Enqueue Message Sink block is used to send PMTs from the flow graph to the Starcoder client. So here's a message strobe just sending PMTs every 2 seconds to the block. And the Starcoder source block gets the PMT message from the Starcoder client and sends it to the flow graph. So here's the block sending any received commands for printing via the message debug block. A flow graph can contain any number of these command sources and message sinks. So you can just communicate with all of them via the same bidirectional stream by just using their ID. So we mentioned that we use PMTs to communicate directly with the flow graphs, but we also mentioned earlier that PMTs only exist in 2 languages, Python and C++. So how does that work? The solution is protocol buffers. Protocol buffers can be compiled to any of the 10 languages it supports, and is the language used by gRPC to serialize data. What we did was we wrote a one-to-one mapping between PMTs and protocol buffers. So a PMT, which we call a block message, can be one of a Boolean PMT, a string PMT, integer, double, complex, a pair, a list, which is either a vector PMT or a tuple PMT, a uniform vector PMT, a dictionary PMT, and we even have a special data structure for a blob PMT. This conversion is done at the C++ level inside the Enqueue Message Sink and Command Source blocks. Now, because of this, any Starcoder client now only needs to know this protocol buffer definition to process PMTs themselves. So just like that, we've effectively extended PMTs from 2 languages to 10. I'd like to relate this to Marcus' earlier talk, where he talked about how PMTs were bad, they were unsafe, they didn't have language bindings, and they were not portable. Well, protocol buffers are safe, they do have language bindings, and they are portable. So that's one idea. One more thing I'd like to explain is how Starcoder actually starts the flow graphs. One thing I haven't mentioned yet is that Starcoder is actually also written in Go. Now, this is a bit of a problem because GNU Radio flow graphs are compiled to Python code, and we need a way to run that. So instead of calling a bash process, we actually embed the Python interpreter in Go. So for those of you who may not know, the Python interpreter is actually written in C. Well, the most common implementation of the Python interpreter is written in C. That's called CPython. And when we run a Python script, there is a C interpreter loop that just reads the Python code and runs it line by line. So CPython actually provides C programmers a rather low-level API to call Python from C, which we call the Python C API. And this lets people call Python functions, import Python modules, instantiate Python classes from C. And Go can actually run C. So by extension, Go can run Python. And so this is what happens when Go code is running a GNU Radio Python flow graph. So starting from Go, we call C via the C API, and then which in turn calls Python, the compiled Python flow graph, which in turn calls the C++, at the GNU Radio scheduler level. So this chain looks like it shouldn't work, but we've proven that it does fine. And so what we do is we actually import the compiled flow graph into Go and call the start, stop, and wait functions on it. And this level of flexibility lets us access the flow graph blocks directly, which we do to let Starcoder hook in directly to the flow graph, particularly the Starcoder Command Source and Message Sink blocks. So what we do is before starting a flow graph, we register a C queue to each message sink and retrieve a C queue from each command source. So in the case of the sink, it pushes messages received by the sink on the queue and Starcoder waits on these queues to send them back out through gRPC. In the case of the source, Starcoder sends commands to the C queues of the command source blocks. So the block waits on this queue to propagate messages to downstream blocks. Yeah, and that's Starcoder. Here's a summary of Starcoder's key features and design decisions. It fully manages the lifecycle of flow graphs from compilation, execution, stopping. Uses gRPC as the RPC framework. All interaction with the flow graph is done via a single bidirectional streaming gRPC connection. PMTs are converted to a well-defined language-neutral protocol buffer format, and it's written in Go. Here are some real examples of how we're using Starcoder. So the first one is Doppler shift correction. So satellites are not stationary. When a satellite is moving towards a ground station at high speed, the frequency perceived by the ground station is higher. And when a satellite is moving away, the frequency perceived is lower. We all know this is called the Doppler effect. So to compensate for it, we need to send the appropriate amount of frequency shift to the flow graph and adjust the IQ data from our radio correspondingly. So in this flow graph, we get the Doppler shift information from the Starcoder client via the Starcoder Command Source block. And this gets passed on to the signal source. And finally, it's multiplied with our radio source in order to adjust the IQ data. Another way we use it is when getting back complex IQ data from a satellite back to the Starcoder client. Since Starcoder currently only works with PMTs, we have to convert the IQ stream into a PMT. So that's the complex to message block right there. And which we then send it back via the Enqueue Message Sink block. Here we have an AX25 transceiver. When we receive AX25 packets from the satellite, we send those packets to the Enqueue Message Sink, which then makes its way back to the Starcoder client. On the other hand, when we want to send AX25 packets to the satellite, we send the payloads to the Starcoder Command Source, encoded with the AX25 encoder block, which eventually makes its way to the USRP sink. I'd like to take this time to give a quick shout out to SatNogs. These AX25 decoder and encoder blocks are actually from GR-SatNogs. So thank you. Maybe you can use Starcoder. Yeah. So here's some room for improvement for Starcoder we want to eventually work on. Right now, we have, frankly speaking, non-existent documentation. Although we just had our first ever alpha release over the weekend, the documentation is still very much lacking since we only have one user, us. In fact, this is the first time we've ever presented Starcoder to the public. The code has always been open source, but we've never really officially told anyone about it until today. We're still trying to figure out if there's genuine interest for Starcoder outside of InfoSellar. So if you're interested in using Starcoder right now, please contact us and we'll help you get set up. Another thing that Starcoder currently only supports sending PMTs back and forth. So if you wanted to work with streaming data, you need to package them into packets, like I showed earlier for streaming back IQ data. Also, all flow graphs currently run in the same process. This can be problematic since a malfunctioning flow graph or buggy blocks can potentially mess with other running flow graphs. For example, if we have some kind of memory corruption bug in one of the blocks, we'll eventually want to run each flow graph as a separate process for better isolation, and so we can also kill them when necessary. Another limitation is that flow graphs only run while the single bidirectional stream is alive. This is because it's optimized purely for InfoSellar's use case, which is multiple short-running flow graphs. So you can't, for example, start a flow graph from an Android phone, turn off your phone for a day, turn it on again, and continue communicating with the flow graph. Maybe this will be possible in the future, depending on interest. Yeah. Finally, we're very interested in tighter integration with GNU Radio. I'm not exactly entirely sure how that would look yet, but maybe we could use some of control port's existing wiring for Starcoder or extend control port with some of Starcoder's features. I'll have to have a chat with the GNU Radio maintainers and see if they think this would be something useful to coordinate with. Yeah, that's it. Thank you for listening. If you want to contact me, my email is right there, or you can just go directly to our GitHub repository for Starcoder, file an issue, and yeah, that's it.
OK, we have time for questions. And if the next speaker can get lavaliered, that'd be great.
Hey, great talk. Thank you. So I guess my question is, have you thought about running, like being able to run processes on different machines. So like have a flow graph that might be on a machine that's 100 miles away that you started with with Starcoder, but it's not actually a local process.
So we actually can run Starcoder on some separate machine. So it's a gRPC connection that works either locally or over the internet.
Okay, so that part can actually traverse whatever network connection you have. Okay, great.
Yes.
Cool, thank you.
You show the several ground stations. Those are all yours, right?
Ours and our partner stations. So we have partner universities and companies, mostly companies.
Okay. Another question is, I'm interested in that example for Doppler that you showed.
Okay.
So where does the calculation of the Doppler come from? That's the part that you didn't get.
That comes from our Go client. So we actually run 2 separate programs in our ground station. Our Go software application, which kind of calculates all the passes and all the Doppler shift information. And we run Starcoder in another process. We then send the Doppler shift information to the.
Okay, so I suppose you use some sort of like predict or something like that for, I don't know, based on TLE estimations or something?
Yeah, we do use TLE data and those libraries.
Thank you.
Additional questions? Okay, let's give a round of applause and thank our speaker.